Welcome to qnawire.
Okay, so we're being asked to show that e of x is greater than 1 plus x for all x greater than 0. So we're going to assume that f of x is equal to e to the x minus 1 plus x. So this is completely normal. You can do this. You can assume any function. So let's take the derivative. So f prime of x, well, that gives us e to the x minus 1. And we know that e to the x is always greater than 1 for all x greater than 0. And you know this because of the graph of e of x. So if that's true, we know that f prime has to also be greater than 0 on the same domain, on x greater than 0. So if that's true, if it's increasing, we know that f of x is also positive. It's not necessarily positive, but it's greater than f of 0 because f of 0 is the minimum point. So we know that f of x, so any number greater than x, which is all x greater than 0, this is true. So, and if you plug in f of 0, well, that's just f of x, and that's just going to be greater than 0 because f of 0 is 0. Oh, f of 0 is, yeah. And so then we can, if we know that's true, then we can actually go ahead and plug in f of x. So that'll give it e to the x minus 1 plus x is greater than 0. And now we can move the terms over to the other side and we get 1 plus x. And it is proven. For b, we're being asked to prove e to the x is greater than 1 plus 1 half x squared for all x greater than 0. So we're going to do a really similar proof style. We're going to let f of x, we're going to let f of x equal e to the x minus 1 plus x plus 1 half x squared. And then if you take the derivative of that, f prime of x equals e to the x minus 1 plus x. Now this looks really familiar, and in fact, yes it is. That is very familiar to our f of x, and we've proven that f of x is also greater than 0. So we can actually imply that e to the x is also greater than 1 plus x. So then that implies that f of x, again, is greater than f of 0, which is just 0. And so we can plug in our function already. So we can do e to the x minus 1 plus x plus 1 half x squared. And this is greater than or equal to 0. And then you can rewrite this by bringing it to the other side. So you got e to the x, which is greater than 1 plus x plus 1 half x squared. And that's our proof. And then for the last one, we're being told to use mathematical induction to prove that for x greater than 0 and any positive integer n. So induction, if you're not familiar what it is, you're basically proving that if it works for, let's just say that this proof works for, so for this case, we have e to the x greater than 1 plus x squared over 2 factorial plus, and then on to infinity or whatever n integer, x to the n over n factorial. So if you think about it, we have just proved it for n equals 0. N equals 0 is factorial, or n equals 1 factorial, which was just this case right here. And so what induction means is that we're trying to prove it for the n plus 1, or the n. So if we know it for the 1th, we know that it worked for 1. The question is, does it work for n equals 2? Does it work for 3? Does it work for 4? Does it work for 5? On and on and on. So basically n plus 1. And that's essentially all mathematical induction is. It's a very clever idea. So this may be a little bit harder to digest, but just think about the ideas. So we're going to do something, again, very similar. We'll let f of x equals e to the x minus 1 plus x plus 1 half, this is 1 half factorial x squared, and then plus, and then it's going to be, we're going to let it equal 1 over n plus 1 factorial because we're looking for not just the nth, we're not just proving it for one n, we're proving it for all n. So by adding n plus 1, we're proving that this works for any n. And so we're going to also replace x to the n plus 1. Now we take the derivative. So the derivative is going to be e to the x, and it's going to be minus 1 plus it's going to be 1 plus x plus 1 over 2 factorial x squared plus, and it's going to be 1 over n factorial times x to the n. We already know that for the regular case, x to the n over n factorial, we know that that's, oh no, I'm sorry. We know that f prime is greater than 0. So we know f prime is greater than 0 from previous proof. So we can actually go ahead and plug in that f of x is greater than 0. Well, it's f of 0, but in this case it will be 0. And so we can go ahead and even plug in our function. So e to the x minus 1 plus x plus 1 over 2 factorial, and that's x squared, plus, and then 1 over n plus 1 factorial, and then x to the n plus 1, and that's greater than 0. And then we move over all that term, so 1 plus x plus 1 over 2 factorial, plus, and then it's going to be 1 over n plus 1 factorial, and then x to the n plus 1. So that's the proof.